Welcome to the Material Minds podcast, a place where we talk to the people exploring new materials for a better world. This episode is going to be a little bit different. We are talking to an INM alum, Professor Phil Egberts from the University of Calgary. He works on lubrication and friction. He was the first PhD student of Professor Roland Bennewitz, our very first podcast guest over here. So we talk about his journey from his time at INM all the way to the science that he's doing and how he gets lost on the streets of Europe. It's a fun conversation and I hope you enjoy. Let's go ahead. So, welcome, Phil. It's great to have you here. So you're coming here all the way from Canada, right? And with like 20 students along with you. What's with that? What brings you back here to INM this time?
Well, so in Calgary, we have a very special program. We have an endowment from the Seymour Schulich at the University of Calgary that lets our undergrad students have experiences, be it going to like building in developing a team, sort of making a race car for a competition, or for example, coming here on this trip to see what engineers and material scientists are doing outside of Canada.
That's cool. And so you thought INM would be a great place to show them something. Did you have anything particular in mind from what we're doing here?
Well, I have very fond memories of working here, and so I thought the students would appreciate the opportunity to come here, and I always like to come back to come and say hello. And INM has excellent facilities, great people working here, and so it's really a great experience for the students to be here to get to see what's happening here in Saarbrücken.
Yeah, that's wonderful. So you've been here as a PhD student, way back, pretty much the first PhD student of Roland's, right? So our first podcast guest.
It's surprising that I was, considering I'm still only 21. So.
Yeah, so you have really fond memories from when you were here. How do you think things have evolved since then?
In terms of my own career, or
in terms of your career, in terms of the material science, the research, and so on.
Okay,
and what you've seen at INM lately.
Well, as we were coming up here, INM has expanded to the other side of the building. So that's really interesting to see. I sort of keep on top of what's going on a little bit when I get to see Roland at conferences. So I hear only like great things. The students that are coming here are really good and doing excellent work. I see their journal publications. It's interesting. I learned a lot while I was here. I had only lived in Canada before, and so Germany was a big learning opportunity for me, not only in science but also learning a foreign language and meeting lots of people and surviving in a different country. And so I look back on it now as this great opportunity where I became more of an adult maybe than I was before, and had a lot of great experiences, met a lot of great people here. So yeah,
that's really wonderful, and I think that's the common experience that people are having still. I hope. Yeah. So you did your PhD here. Can you say anything about like what you worked on and where that led, how that led you, across the world to different places and then eventually Canada?
Okay. So I came to work for Roland on the recommendation of a professor I was TAing for in Toronto. They had excellent scanning probe microscopy at McGill, and Roland then came here, took a new position here, and then the European adventure started. And I was working mostly on looking at plasticity in crystalline materials and seeing if we could measure or create single dislocations in these crystals.
Okay. What are these crystals? Are they materials that I know of? Or?
So we were looking at basically pieces of salt.
Oh, okay. I know that.
Yeah. And so like, the salt you put on your foods, it's not the same salt, but pretty close. And we looked at those because they had big atoms in it, so the dislocations would be bigger. And it was really easy to make flat surfaces of these.
Okay.
So Roland had spent a long time looking at salt crystals for other applications for the similar reasons that they have big atoms and they're easy I would say easy in quotations to prepare.
Yeah, okay.
And so we looked at those for a long time, lots of different ways of looking at them. And we also then looked at some metals. So those are a bit trickier. The atoms are a bit smaller, so you have to have the measurements perfected a little bit more. And the big thing that happened at I&M was partially I had to learn to get better at computer programming. At McGill, we had a really great system, but to do the experiments, you had to start something and then click about 40 switches in the right order, and then do a different experiment and then turn the switches the other way around. So if you didn't have enough coffee that morning, you might have missed a switch or two.
Yeah.
And when we came to I&M with the research facilities here and like sort of the program that was offered to Roland, we really upgraded the electronics on the microscope so we could automate all these things, and you could have less coffee while you were doing this experiment.
Okay.
So,
But that means you were part of automating it. Like
Yeah.
when you say you had to learn coding
yeah.
to do that. Okay, that's really cool. And has that helped you since?
I recently had a group meeting in Calgary with my own students. I probably, this is an overshare, they'll be embarrassed if they see this, but my students are all really lovely students and they're all working very hard. And I say every group meeting on Thursday, could you please have results to show what you've done to the other students so we can talk about it. And quite often they're spending until 2 or 3 in the morning trying to analyze their data so they look like they have something to contribute to the discussion.
Yeah.
And I often feel really badly for them because they're not using computer coding or something to make their job more efficient. And so I've done some extra lectures now with them. And I'm not an amazing computer programmer. I'm more like, you could program something so you can drink more coffee, not in the lab. And I told them if they work on this a bit more, maybe they could sleep more. So
That's a great motivation.
Yes.
Yeah. And I think that's the way a lot of things are moving. Also at I&M, we're expanding our capabilities to automate a lot of the research that we're doing and go into more high throughput kind of research. And of course, programming plays a pretty big role there.
Yeah.
But let me get back to what you talked about, plasticity in these crystals. What do you mean by that as such?
So if you take a piece of metal, like you're building IKEA furniture or some other furniture, and you get frustrated and you accidentally bend it too much, that's plasticity. So once you push down on it and it permanently bends, that's caused by dislocations moving in materials. And so we wanted to really look at where does that start in a perfect material, and what are the forces involved to do that. And it was a really interesting topic that not many people looked at, and it was kind of complicated also because Roland and now myself, we worked in the scanning probe community, and quite often that community is a little bit separated from mechanical testing community. So it was also trying to sort of straddle these two fields and bring them together so we could talk a common language.
Okay, so then you're working at, like, let's say the atomic or the micro nano scale, right? And are you able to translate what you learned from there into this macro scale, like how you say bending a metal bar?
So we did spend quite a considerable amount of time doing that. I would say we had moderate success in that. And I think when I finished here at I&M, I decided that was really hard to do. So I decided to sort of switch gears and go more into tribology, which is also what Roland was doing here at the same time. And when I left I&M, I went to work for Roland's biggest competitor / very good colleague in the United States. And I spent a lot of time, actually Roland and my postdoc advisor, Rob Karpik, were the people that sort of started first examining mechanisms of lubrication using graphene. And so that's really where my work now at the University of Calgary has gone, like continuing that work to look at how graphene can lubricate surfaces and how one layer of atoms changes a lot of things, but sometimes also 2 or 3 layers changes things even more.
Okay, that's interesting. So your work now kind of has built up from your work a bit at I&M and a bit at in your postdoctoral lab. So lubrication, is it mainly graphene that you're looking at now, or are you looking at it more broadly in a sense?
So we look we're looking at graphene and other 2D materials. We've started branching out into newer 2D materials. So I have a student right now who's looking at sort of the most exciting one of the most exciting 2D materials. There's many of them, but we're trying to make mech scenes in-house and really understand them. Hopefully we can also look at chemistry of the surfaces. And my colleague said Calgary will laugh because I usually try to avoid any chemical reactions. 'Cause I don't work in a chemistry lab usually.
Yeah.
And I've also been trying to work with colleagues on bringing the really, precise and great techniques learned or that we can use with AFM to measure friction to biological materials, or expanding also the knowledge and the background to more industry relevant materials. So like an oil or a grease.
Okay. But this is a pretty broad spectrum. If you talk about biological materials, is this like bone or so that you're talking about, or where's friction the most interesting there?
So I have usually when I go into these more broad areas, I have to have a very good friend and colleague to help me. As I said, I try to avoid going to chemistry labs and rather just measure things. So I have a colleague, Mariam Badev, who is looking at surfaces that you can implant in the body that are lubricious. And in particular, I think you can also look at like protein functionality, where you can change the surface depending on what's absorbing on it, or that it can also prevent absorption of certain biological materials. And so we're just really in the beginning of this. I'm definitely not the expert in that. I'm looking at it because we can use AFM and the associated techniques that we've used in graphene, for example, to do similar characterization on these materials. And I hope that it becomes a longer term exciting area of research for the two of us to work in. So
that sounds really interesting. So this is generally just like an implant. You want to make it as lubricious as possible.
It's a soft material. I would say,
Okay.
from my ignorant position on this, I would say something like a hydrogel.
Yeah. Okay.
They're using, for example, cellulose
to
coating these cellulose surfaces in a lubricant. And so it's as I said, I'm still working on learning everything about it, and I rely on support of my collaborators for learning all these things.
Sure.
Go.
And on the industrial side, you talked about oil-related applications. So is that like to grease the wheels in a machine, or what is it like?
Yeah. So when I was working for Roland, I was in the Department of Physics at McGill, and I really didn't work so often with industry. And I moved to Calgary, and there's really great industry in Calgary. Calgary is also a very innovative university. They have they're well known for knowledge translation, IP generation, startup companies. And I guess when I started there, I felt a little bit underprepared to do that kind of work.
Yeah. Okay.
And it was something that I had to work on, and it's still not something that I have a great strength, and I'm still working on it. And I had worked with Calgary's also really well known for oil and gas companies. So we have the oil sands in Alberta. And so I started trying to work with these companies, looking at developing testing mechanism or methodologies for the fluids they use to lubricate the drilling equipment there. That was not as successful as I hoped for, but I did sort of meander around meeting people, and there's a great company in Calgary that is the largest producer of greases in Calgary, and they were looking for some different ways. We haven't officially worked together to develop new lubricants together, but they are really interested, for example, in greases for rail tracks that switch back and forth. And replacing additives such as lithium that are harmful for the environment. We also want to save lithium for electric batteries. And so with another colleague also who is much better at chemistry than I am, we're looking at using more sustainable materials, so cellulose and clays as the materials that can thicken an oil into a grease, for example.
Okay, so Apart from sustainability, where are the big challenges actually in actually getting good lubrication, machine parts, or wherever we want?
Yeah, so in a conference that like Roland also often goes to, there was a great talk a few years ago from another professor at the University of Pennsylvania, which is where my postdoc was at, where he showed how the Ford Model T required almost daily maintenance. So you go for a drive and you needed to change the lubricants and all this stuff. And he compared it to his current car. Like many people just drive their cars and then they're like, oops, I forgot to take it in for an oil change when I change my tires for the winter or the summer. And so you can just see through these two examples the advancement in lubrication and also the life cycle. So lubricants are really important for ensuring that machines don't wear out, right? And so there's been great advance in this area, but still it's really hard to design a lubricant in advance knowing how it's going to impact the machine. So we know from our experience, kind of like artificial intelligence can guess what's going to happen in the future, but we don't have good equations or good scientific principles to describe friction. And so first off, if we could do that, then we could know what kind of materials to mix together to make the best lubricant available. But even with our sort of, let's say, less predictive ability to engineer lubricants, there's a great deal we can do to reduce the impact of humanity on the climate. So significant amount of energy that is used in combustion engine is lost to friction and wear. So you can see that you also have to like change your oil all the time, and that's disposing of the oil is a lot. And then your car like only lasts 10 or 15 years. Part of that's also because the components wear out, so the lubrication isn't perfect, right?
Yeah.
You can also think about like it's cold outside right now. It's much warmer here than in Calgary. It's minus 25 right now, and you don't want to have a car accident on your way to work.
Yeah.
So you might want to figure out how to design a tire so that it's sticky on ice, but also not too sticky that the car will use more engine. So all these kinds of things. I talked about rail greases before, but so many different applications. As we look to the future, we need to think about how we're going to lubricate electric engines as we increase the voltage of the battery packs and a whole bunch of other things. Hopefully we can make an impact on like the range of electric cars through lubrication. I've focused mostly on cars. I'm in mechanical engineering. All my students are super excited to see German cars while they're here. So I guess I have that on my brain. But yeah, so that's where I see the application in the future. But we can also improve wind turbines or power generation through wear-resistant coatings and all kinds of things that we can do in lubrication science.
Yeah, that's really fascinating, and it's very interesting for me to learn that there aren't really good equations to understand this and be able to design lubricants ideally. And I guess is that part of what you're also working on to try to get into the fundamentals of these aspects?
So that's the main idea of doing the more basic science, not so applied to industry where you could buy it at the store. The idea is if we know that friction comes from atoms touching other atoms and sliding across them. And if we can look at materials with the precision that we can with the atomic force microscope or other nanoscale techniques, then we can start to get insight into seeing what's going on. So unfortunately, you can't see the sliding contact usually in AFM. So there's other colleagues that are in the field, and they try and look at these tiny contacts sliding against each other with an electron microscope like you have here at INM. So they can also see like how the atoms are moving around while they're sliding against each other. And then there's a lot of work here with computer simulations, and I like to work with these people. So the experiments that I do in the lab are sort of designed around can we work with a simulation group to recreate what's happening. And I like to think of simulations as like dumping humanity's knowledge into a computer and seeing if that looks the same as our experiments. And it's really interesting when it's not the same, because that means that we have more questions to look into. So.
Knowledge is incomplete.
Yeah.
Basically, at that point. Yeah. Interesting. So in your journey, now you're doing all these things. In the middle, you were back in Germany for a year or so, right, as a Humboldt professor. What is that stint about?
So I lived in Hamburg during COVID. It was an interesting time. I went to work with Roland Bennewitz and Alex Schwartz in Hamburg, and they have really expertise in designing surfaces that are like quantum surfaces for quantum information and storage. And they had done some, I haven't thought about this in a while. They had done some experiments with scanning tunneling microscopy, where they could see features that look like atomic friction experiments. And the problem with tunneling microscopy is you can't measure forces, and without a force, you can't really relate it to friction, but you can do a simulation or something in that way. So I went to Hamburg to first off have some fun in the lab, because I hadn't, when you become a professor, you have less time to go to the lab. They have really, really cool, enormous microscopes there that I got to work on. And I was going to measure friction on these very interesting surfaces, sort of at the bleeding edge of friction, like looking at how quantum impacts friction, which is not something most people consider in tribology. So
yeah, okay, that's really fascinating. It's a really good opportunity then that you had at that moment. But talking about German cities, for example, like Saarbrücken, Hamburg, and now you've been in Pennsylvania, you've been in Calgary in North America. I've heard some stories from your past about how it is difficult to navigate through cities that are not sort of quadratically organized, where things are a little bit more winding, as it is more often in Europe. So how was your experience in Saarbrücken with that, finding your way around, and how has it evolved ever since?
Yeah, so I when I think back on it, it's really funny. So I think of gummy worms. I think if you sprayed them on a table, that's how the streets look like in Europe. So they're all everywhere. And I grew up in Toronto. Toronto is on a grid system similar. I lived in Montreal before coming here. And so I moved here and I got lost for 3 months trying to go from my apartment to the train station, because there were so many different ways you could go that were almost the same amount of time of walking. So it took me a long time to figure that out. I also remember having fights on the Autobahn with people being like, okay, we need to go west to the airport, or east, sorry, it's east to the airport here. And so how do we get on the A4 going east? And you in Germany don't go east, you go to the city. The city's on the way to the airport. And so that was a big learning experience for me. So the only thing I'll say is I can walk around Saarbrücken, but usually I have to have my phone or the Navi on my car so that I can find my way, because I still haven't exactly figured out how you're supposed to know how to get somewhere without the Navi.
And I completely relate to that. I have the same issue. Luckily, when I came here, already GPS and navigation systems were very well established. I'm gonna have a last question to end this. Maybe it's a little bit of a tricky one, but along these lines, with these kind of chaotic road maps and then the more organized ones in the West. Do you see any parallels between that and work with friction on surface and so on? Do structures play a role in that sense, in order and organization?
So it's interesting you asked this question. So when I moved to Calgary, I had always worked with groups that were looking at solid materials, and Calgary did not have so many people in metallurgy when I first moved there. They were mostly the material scientists, similar to I&M, were working in polymers and squishy materials. And my colleagues at the University of Calgary, in particular in chemical engineering, they were always telling me, "Oh, come to the dark side. You do the squishy materials. They're more interesting. I mean, especially if you're looking at bio applications, right? All the materials are squishy. And it's really, really hard I find it's really hard to switch gears to think that way because, as I guess my background more in metallurgy and hard materials, you have a very fixed idea of what microstructure is, how the atoms are arranged, what a grain looks like, how a dislocation moves. And my colleague that I work with on greases, so Milana Trevkovic, her expertise is really in looking at the microstructure of squishy materials and how they change when you shear them or squish them. And it's really hard for me to think about, like, what is microstructure in a soft, squishy thing that keeps moving around much more freely than like a metal. And so maybe in 50 years or so, I'll figure it out. I'll just keep picking at it, having coffee with her to understand what that means. Talking also to my other colleagues that are looking at these materials, and slowly, maybe like the streets in Germany, I'll figure out how to get around these things. So.
Yeah, that's wonderful. Yeah. On that note, I'd like to thank you for coming over and doing this with us, having this really wonderful conversation. I hope you have a great stay over here. If you want to say last few words, please go ahead.
Well, I just wanted to say thank you to you and to everyone at INM and also the people in Saarbrücken. That it's really funny. The students were kind of like, why aren't we going to Amsterdam or Berlin? And I said, the people in Saarland are really, really lovely. They're super friendly and nice. And I've always felt super welcomed here. And it kind of felt like coming back home a little bit when I got here. I haven't been for like almost 10 years to Saarbrücken.
Yeah.
We had COVID and all these other things. And so I would like to really say thank you to the people at the INM. It was really nice to see Elka downstairs at the front desk and Dilka, sorry. And see all the familiar faces of the people that are still here, even though it was a very long time ago I was here.
Yeah.
And it's really nice to be back.
That's beautiful. Thank you. And I hope you have a really great stay here in Saarbrücken, and a good stay and a good actually experience for all the students visiting different places in Germany.
Yeah, thank you.
All right. So with that, I'd like to say thank you for watching. Thank you for listening. We're on YouTube. We're on different social media sites. Please have a look, follow us, and catch you in the next one. See you.